So in this video, we're going to be looking at vapor pressure and solubility. These are two different material properties that are heavily dependent on intermolecular forces. So let's look at some of what we've paid attention to before. So looking at our liquids, we know that we have molecules that are relatively close together, right? There are intermolecular forces that are present there that are holding them together. And in the gas phase, right, we have these molecules that are separated relatively far apart. No significant intermolecular forces are going to be present in that particular case. And so when we go from the liquid to a gas, we've often talked about that in terms of boiling, right? That means that boiling point is actually a pretty good proxy for intermolecular force strength, right? Because the more energy that's required to overcome those intermolecular forces, the higher the boiling point is going to be. Well, that's what we've talked about so far. We want to sort of step back just a little bit and look at vapor pressure. So let's consider vapor pressure. So vapor pressure, we can explain when we have liquid water in a container. What's going to happen is some of those molecules of liquid are going to be able to get into the gas phase. This isn't necessarily boiling, it's just a few of them are able to do that. And so some of those molecules will get up into the gas phase, they'll have enough energy to overcome their intermolecular forces, and so here we have these black dots representing water molecules that are now in the gas phase. Those are then going to exert some sort of pressure that in the system is going to push the mercury just a little bit, and that's going to create a difference in pressure here. And that difference in pressure is then what we call the vapor pressure. Eventually what's going to happen is we're going to establish an equilibrium, and as many molecules that are going up into the gas phase are going to be coming back down into the liquid phase. And once we've hit that, now we'd say that the vapor pressure is constant, and we'd say that's the vapor pressure for this liquid at whatever temperature it's sitting at. And if we vary the temperature, we'll see different vapor pressures. So let's see if we can understand that just a little bit of why that might happen. Right, so we know that at any given temperature, we're going to have a different distribution of molecular speeds, or molecular particle speeds. And so we can imagine at our 273 Kelvin, we're going to have some distribution. Let's just say it looks like this. This is the equation that you'd use to get it. We're not really going to care about that. But what we can imagine, though, is there's some temperature at which a molecule can vaporize, that it can overcome those intermolecular forces. And let's imagine that this delta H of vaporization is sitting right here. What that actually means to us is that these molecules down here, represented by the area under the curve, those are going to have enough energy to be able to escape into the vapor phase, right? They're going to be able to get into the gas phase because when they hit the surface, they have enough energy to overcome the intermolecular forces and blammo turn it into a gas. So that's why we actually have a vapor pressure at all. But we can think about how vapor pressure might change with temperature, right? So at different temperatures, we end up with very different distributions, right? So the lower the temperature, the more molecules have a lower speed. Right? They're just in general moving a little bit slower, right? So the average is a little bit slower. At high temperatures, we have more molecules that we have an average higher speed, so more molecules are at higher speeds. And so we can again go back and find our 273. We see this is the little segment of molecules that would have been able to get into the gas phase if we were at 273, and obviously if we're at some of these other temperatures, 800 or 900, then you have a much larger percentage of those molecules that are able to get into the gas phase, whereas if we're at 73 Kelvin, what we'd see is almost no molecules would have the ability to get into the vapor phase at that point. So again, what we'd get this is the sense that as we increase the temperature, the vapor pressure should increase. And so we can look at a graph of vapor pressure versus temperature. And so we do get that sense. So here's water, and what we see is vapor pressure starts pretty low, and then it starts climbing up notably, and then kind of keeps shooting up. One point that's often of interest is the boiling point. The boiling point we define to be that point in which, or the normal boiling point, we define to be that point at which the vapor pressure of the liquid equals the atmospheric vapor pressure, or 760 millimeters of mercury in this particular case. And that happens for water right at 100 degrees, and so you probably already know that the boiling point of water is 100 degrees Celsius. And so we can actually look at that with other molecules. So for example, we have diethyl ether. What we see is that has a much higher vapor pressure at any given temperature than ethyl alcohol, which has higher vapor pressures than water. And so usually these things sort of follow curves with each other. And what that means is that, well, water actually is sticking together a little bit better than ethyl alcohol, right? It's easier for ethyl alcohol to overcome its intermolecular forces and get into the vapor phase. So what we see is that the weaker the intermolecular forces, the higher the vapor pressure is going to be. And conversely, what that means is the lower the boiling point, right? Because the amount of temperature or the energy that's required to be able to have a vapor pressure of 760 millimeters of mercury is a little bit lower for diethyl ether than it is for ethyl alcohol. And this kind of makes sense. Again, if we sort of think about it, right, this idea of boiling is when we're going from a liquid to a gas. So this idea of that normal boiling point being 1 atmosphere, well, what that's really saying is, well, we've got an equilibrium that's happening between the liquid and gas right here in this vapor bubble. And when that has enough pressure to just push the atmosphere out of the way, that's when the molecule actually starts to boil. And so what that means is, again, our intermolecular forces actually help define and explain the vapor pressures that we have and the boiling points as well. So let me have you take a few moments and actually figure out how you would rank these compounds from the lowest to the highest vapor pressure. So again, remember, we want to look at the intermolecular forces and then think about that relationship between the strength of the intermolecular forces and the vapor pressure. So take a few moments and answer that question on the Google form and then come back. So hopefully you've had a chance to answer that question. You'll be able to explore that just a little bit more in class and try to refine your understanding just a little bit more. So let's look at another aspect of intermolecular forces playing out in terms of some of the properties. And for this one, we actually want to look at solubility. So what we can imagine is we might well have a liquid solvent and solute crystals, and we're curious, well, will these things dissolve in each other? Well, if we think about what needs to happen in order to form a solution, is we have a couple pieces that need to occur. First of all, those solvent molecules are going to have to spread apart. We can think about that as it's going to take some amount of energy just to pull them a little bit apart, make some spaces. We're also going to then have the solute that's going to need to spread apart, and then we're going to have mixing that needs to occur, right? So we need to spread out the solutes and allow them to be able to then interact with the solvent. And in order to be able to do that, we have to spread the solvent out so there's room for those to do. And so when we think about this process, we really need to disrupt the solvent-solvent interactions, and we need to disrupt the solute-solute interactions. And you know that that's going to require some amount of energy to be able to do so, right? To actually disrupt those intermolecular forces. But we're also going to have new intermolecular forces get formed. And so that's going to release energy. And that's a favorable system, right? Because most things happen because we actually get to a more favorable or lower energy state. And that's what actually drives things. So it's really the balance of these things that's going to be particularly relevant. So what we're curious about is, will a solution form? Well, if the solvent-solute interactions are much stronger than the solvent-solvent or the solute-solute interactions, then typically what we're going to see is that the solution is actually going to form. If, on the other hand, or if we get a situation where the solvent-solute have very similar kinds of interactions as the solvent does with itself or the solute does with itself, then again, we're also typically going to see a solution form. If, on the other hand, the interactions between the solvent and the solute are weaker than those between just the solvent or just between the solutes, then it depends on whether or not we're going to see it. It's much more common that we might not get a solution to form, but there are some situations where it does. And in those cases, it's actually driven by entropy, which is something we'll talk a little bit more about next semester. So with this, you'll be able to tackle some of the questions and have a basic understanding of whether or not solutions are likely to form and see the relationship that this has to intermolecular forces.